Hello everyone, welcome to DataXe presentation. DataXe is a system for application self-optimization in serverless edge computing environments. If we look at the picture, we see that DataXe is a middleware located either on a 5G edge, cloud, or spanning edge and cloud. In DataXe, streams will start from sensors such as visual cameras or wireless sensors, fiber, thermal, and so on. Those streams will go through several transforms that will augment them, for example, detecting phases from a stream of frames, or will fuse them, for example, merging visual and thermal views of the same scene. And finally, those augmented streams can be displayed in a user interface, can be used to derive the insights, or can be used to drive actuators and gadgets. What makes DataXe unique is the ability given to the developers to build complex multi-sensor applications by chaining simple analytic units. Multiple analytic units can be dynamically connected on the flight. AUs just operate on the streams to which they are connected. They don't need to be aware of the source of those streams or which AUs will use the generated augmented stream. As shown in the figure, the drivers in DataXe connect to the physical sensors and generate streams to which the AUs can subscribe and use. AUs can subscribe to multiple streams, either generated by drivers or by other analytic units. DataXe provides also some APIs for applications which live outside DataXe to consume streams generated by driver or AUs. For example, analytical dashboard and so on. Some of the main features in DataXe are that the computing infrastructure and the data movement is managed by the middleware by DataXe, hence the developer will just focus on the business logic. And to create an augmented stream is often sufficient to provide a simple script with zero boilerplate code. It gives flexibility in programming model and libraries, so the developer can choose the programming language and the libraries that prefers. DataXe will provide scaling and best performances out of the box. And finally, DataXe is built on standard components in order to avoid to reinvent the wheel and focus on policies rather than mechanisms. So the high-level research goals of DataXe are to provide a simple abstraction to realize distributed analytics applications. In this way, developers will focus on business logic. It will be optimized out of the box for 5G deployments. And using DataXe, developers can bring new analytics applications to market an order of magnitude faster. Other research goal of DataXe is to focus on policy and utilize a standard mechanism, which means we will use popular containers management systems, for example Kubernetes, and we'll leverage AI techniques to solve complex system problems. Here we see some of the research challenges that we are facing at the moment and for which DataXe provides some unique technologies. First challenge is to provide scaling that makes sense for the application, which means take into account the complex topologies of applications and scale based on the metrics that make sense for the application rather than just resource consumption. Other challenge is to communicate what matters, which means that for real-time applications, it's more important to process the most recent data than all the data, and also reliable common messages, queues, and bus that provides just once, at least once, and at most once, incurring high overhead for analytics applications. Another challenge is to manage accelerators in a distributed environment. In fact, we don't want that the developers carry the burden to manage the accelerators during deployment, and also the common use policies of exclusive assignment of an accelerator to a single instance of a microservice incur in very high cost and low opportunities for scaling. One of the unique technologies contained in DataXe is the so-called autoscaling that makes sense. The picture shows an example of a pipeline, very common pipeline, which is phase detection followed by features extraction. The first microservice in the pipeline has a low variance of resource requirements based on the content, while the second microservice has a very high variance of resource requirement based on the video content. Using state-of-the-art autoscaling, it won't be efficient. In fact, state-of-the-art autoscaling, such as Kubernetes HPI, is unaware of microservices dependence. And the user still needs to provide information such as the minimum and maximum number of instances to run. Moreover, the scaling is always driven by resource consumption, and for example, they tend to assign more resources to microservices that uses more resources. And with this approach would work if we would have an infinite amount of resource available. But we observe that in practical system it ends up wasting computation by assigning more resources to phase detection, while feature extraction cannot keep up processing the input. From the other side, the DataXe it is aware of the topology of microservices and tries to optimize the application metrics such as latency, processing rate. It uses AI techniques, specifically reinforcement learning, to decide how to scale the microservices. In this way, we minimize the amount of wasted computation, and this technique will outperform Kubernetes in Kubernetes HPA in all the practical deployments. The state-of-the-art communication mechanism between microservices is either messages bus or queues, or direct communication. They both have pros and cons. Messages bus are easy to extend, but they incur in high communication overhead, and also the consumer's microservices need to implement the logic for skipping unneeded messages. From the other side, direct communication has much lower overhead, but there's the problem that microservices need to be aware of each other and need to be developed in a way that they are aware of each other. DataXe tries to provide both the pros of both kind of mechanism. In fact, it exposed to developers the same semantic and extensibility of messages bus, and it uses AI model to estimate the processing rate to avoid wasted communication while keeping the consumer's microservices busy. The DataXe communication technology is completely transparent to the developers. In fact, it used the technique of sidecar. So basically, they will run side by side with the user application, and it will provide the benefit of messages bus and direct communication.
Coprocessor.
No, it's my coprocessor.
No, it's mine.
No, mine.
It's mine. Give it back to me.
Guys, hold it. I have a great idea. Why don't you share the coprocessor? Yes, share.
As Kermit the Frog suggested, we can share accelerators. And that is part of the unique technology provided by DataXe for automatic accelerator management. DataXe provides an abstract API for requesting accelerators. Basically, the AUs, the microservices, will just need to declare which API, accelerators API, they can use rather than request directly the device. Then we have technology in DataXe for sharing accelerators. In fact, the common way, the state of the art today, it is to just assign one accelerator device to a single instance of a microservice, which will provide, will limit the scalability and lower the system performance. DataXe measures the accelerator resource availability, the microservices utilization, and using AI models finds instances of microservices that can share the same accelerator. Finally, in DataXe, we introduced the concept of optional accelerators. In fact, following that popular AI ML libraries such as TensorFlow or PyTorch support using the same model with or without GPU in their case, AUs can declare optional requirement for an accelerator. In this way, DataXe can, using AI models again, can decide which how many instances of a microservice will be assigned with an accelerator and how many will run without accelerator. This picture gives an overall idea of the interface that the user has with DataXe and what DataXe does to deploy the applications required by the user. So first of all, we see in the top, the user will just submit to DataXe a topology of AUs of microservices and a bunch of sensors to use. From there, DataXe will use internally as AI models to optimize the communication, the autoscaling, and to manage eventually accelerators. So if we start, we see that first of all, DataXe will create instances of drivers to collect data from sensors and make streams. Then we'll have a whole layer of communication that are implemented inside DataXe sidecars, and which the communication will be managed using the AI model inside DataXe. Then DataXe will scale appropriately the microservices, and it will manage the accelerators. Recently, we have ported the action recognition application Eigen from the machine learning group of NLA to run on DataXe. The standalone version can be run as a single container, and the application manages internally the multiprocessing. The application itself, it is already composed by some independent modules, which are the coarse-grained and fine-grained analytics of the frames, and the frames are analyzed independently by these two modules, and finally the information are combined by this SDP attention module that will recognize the action in the video. So here, if we take a look what was the action recognition application before and after porting to DataXe. So first of all, we see the top of our figure are the actual application modules, the business logic, which is exactly the same before and after, but the standalone application needed and had to take care of a lot of system level problems. For example, the multiprocessing, the multithreading, and the inter-process communication, which had a custom module for that, had very limited scalability opportunity since it was running as a single container. there was almost none support for reliability, software updates, and it could and it did use GPUs, but it was a custom support for accelerators. Now, when we run this application on DataXe, we just keep the business logic, and all the system level optimization will be taken care by DataXe. Here we show a small video of action recognition. We see that the same video is fed to the same business logic, but one runs in the standalone fashion, so the legacy application, and the other on DataXe. We see that when we run it on using DataXe, using the same hardware, we can recognize more actions and quicker. When we do a quantitative analysis of the performance of action recognition, standalone version and the version that runs on DataXe, we find out that the DataXe version using the same hardware can process about 3 times the number of frames compared to the standalone version. This figure shows some deeper understanding of the performance changes in the application. So the first plot, in the first plot we show that on average it takes the same time to process each frame both in the standalone and in the DataXe version, which is not a surprise since they use the same hardware and the same business logic. But we see that in the middle plot that when we use DataXe, the application spends a lot more time doing useful work, processing the frames rather than managing the multiprocessing or communication between the processes, which we see in the last plot will lead to the increase in throughput. Thank you.